Hello everybody, welcome back. This is Dr. Rhonda Kofelt and this is the part 3 of acids and bases. And in this section we're going to learn how to calculate pH and pOH, and then we're going to calculate H3O plus for a weak acid using Ka. And I'm going to also introduce to you the pH square. So how acidic or basic something is expressed typically in pH. And the P in pH, or any other thing you see in chemistry, means the negative log of whatever follows that. So pH is the negative log of the hydrogen ion concentration, or remember we can interchangeably say hydronium or H+. So the negative log of the H+ in your equation. The exponent on the 10 is going to be a positive sign. So what happens is, if you're doing the pH of water, that would be the negative log of 10 to the minus 7, which is the molar concentration of hydrogen ions in pure water. And if you do negative log of 10 to the minus 7, and you put 1 times 10 to the minus 7 if you want, that's going to give you 7. And so if it's 1 times that number, this exponent, if you change it to the positive, will tell you what that pH is. So we need to know what the H3O plus concentration, or the H plus, if we're going to find the pH of something. And remember, pH of less than 7 is acidic. pH of greater than 7 is basic, and then the pH equal to 7 is neutral. If we know the pH, we can also determine what the H3O plus concentration is by saying 10 to the negative pH, and that'll give us the concentration. So we're going to work problems doing both things. So when you think of pH, don't get bogged down in the numbers so much as this. If you have the H plus concentration, okay, the higher the concentration, that is the farther from 10 to the minus 7 you get, the more acidic. Because remember, 10 to the minus 6 is a higher number than 10 to the minus 7. And 10 to the minus 0 is 1, right? So that's how you interpret this. And then going the other way, the farther you get from 7, the more basic you are. Same thing for pH. 7 is neutral. So the farther you get going down, the more acidic you are. So 5 is more acidic than 6, and a 1 pH is much more acidic than a 5. And then on the basic side, it's a little bit easier to intuit, because the farther away from 7 you get, you're going up in numbers, and that's going to be the more basic. So 7 is neutral. The farther you go away from 7 and go down, the more acidic it is. The farther away you get from 7 in increasing numbers, the more basic it is. Okay? So to calculate the pH of a solution at 25 degrees C, when we know first the H3O plus. So we know that pH is equal to the negative log of the H3O plus. So the negative log of 1.8 times 10 to the minus 4. You have got to make sure that you can put this in your calculator correctly. That negative sign right there is the one that's usually found down at the bottom, that's in parentheses, okay? That's how you change the sign. And so you put in negative that way, and then you push in the log button, and that'll bring up parentheses, and then you would type in 1.8 and then EE minus 4 if you're doing it like I've showed you in the past. Ever how you do it, when you put that in your calculator, you need to make sure that when you put that one in, that you get 3.74, okay? So that's the number you should get when you put that in your calculator. And since that's the pH and that's less than 7, then that must be acidic. On this one you have the OH, okay, and you can do this a couple of ways. We've already learned about the KW, right? So if we know the OH, okay, then we can find the H3O plus, because that's what pH is determined by. That's going to be equal to our friend 1 times 10 to the minus 14 divided by the OH concentration, which is 1.3 times 10 to the minus 2. And that is going to give us 7.7 times 10 to the minus 13. Okay, and that is the H3O plus. So then we take the negative log of that in our calculator, and that should give us 12.11. Now there are other ways to, and that's a base, right? Because of that pH is higher than 7. Okay, so in order to find pH, which is what we're looking for, you've got to figure out what the hydronium ion concentration is. So if it gives you the hydroxide, we've already shown you how to use KW to find out what the hydronium ion concentration is, because that's what you would take the negative log of to get the actual pH. So if we're going back, okay, and this one can be a little tricky, so you've got to understand how to use your calculator. Instead of doing the negative log, we're going to have to do the opposite function, okay, which means that we're going to say 10 to the negative pH is going to equal that H3O plus. So in this particular problem, 10 to the negative 4.80 is going to equal your H3O plus. And so when you put that in your calculator, you should get 1.6 times 10, and it probably had another, it may have been 0 on mine, times 10 to the minus 5 molar. I should have done that to three significant figures, and I didn't. Okay, but anyway, so it should be somewhere around this number, okay, and it should definitely be somewhere around 10 to the minus 5. So that's how you go back. If you know the pH, that's how you get the H3O plus. This is going to be important when we start looking at weak acids, because we've got to be able to figure out what this H3O plus concentration is in different ways. And if they tell you the pH, that's a really easy way to figure it out. There you have a practice doing the same thing. Now, you can also have, in addition to pH, you can have POH, right? And we've already seen that as one goes up, one goes down. So on our pH scale, we're going down to 0 for pH for acids, and we're going up to 14 for bases. And so that's based on pH. If it's POH, it's going to be exactly the opposite. You're going to have your 0 down here and your 14 down there, because as you go one way or the other, they're going to change. If you need to know what the POH is, again, you take the negative log of the hydroxide. If you need to know the hydroxide and you have the pH, you do 10 to the minus POH. All right? Because the POH of pure water is 7. Since we know that, here's a nice, handy, easy thing. If you know the pH, we know that the pH plus the pOH has got to equal 14. So if you know the pH, you can subtract that from 14, and that will give you the pOH. If you know the pOH, then you just say 14 minus pOH, and that'll give you the pH. Okay? Because it's that 1 to 14 rule, 10 to the minus 14 for the kW, right? And 14 for pH. So when we're looking at acid-base reactions, another way to talk about the strength of the acid would be its pKa. All right, it's pKa. The stronger the acid, the smaller the pKa. Because the larger the Ka, the smaller the pKa. Okay, because the pKa is the negative log of that. And it's the same thing with the base, except we call that a pKb, which is the negative log of the Kb, which again, remember, is the ionization constant of a base, or the ionization constant of an acid, depending on if it's Ka or Kb. I'm introducing this to you right now because the pH square is a really handy tool. And you're welcome to use this on the test if you need to be reminded. But what it does is, if you're going from a base to an acid, you follow the red arrow, and if you're going from an acid to a base, you're going to follow the blue arrow. So the way this works is, if you have pH and you need to go to the H plus, you're going to follow this, and that means that the H plus is going to be equal to 10 to the negative pH. Right? If you need to go from H plus to OH minus, it tells you that those two multiplied together is equal to 1 times 10 to the minus 14. So see how that works? And then down here, going from pH to pOH, pH plus pOH equals 14. So it's a really nice graphic to remember how these work, because when we get to some of these weak acid problems especially, there's going to be more than one way that you can get to that. Okay, more than one way you could figure out what the H3O plus concentration is when you're doing it. Another interesting thing that we're going to see when we're figuring out, is it a strong or weak acid or base, and how that's going to impact the equilibrium of these reactions, is called percent ionization. And percent ionization is how much of the acid is ionized to the H plus. And so the percent ionization is the molarity of the ionized acid, which is your H plus concentration, divided by the molarity of the acid, which is, HCl, H whatever, times 100, and that gives you the percent ionization. And since they're in equilibrium with each other, the H3O plus at equilibrium divided by the HA initial, the initial concentration, times 100 is going to give you that percent ionization. So whatever that original molarity is of your acid, and then whatever you calculate the H3O plus to be, the H3O plus at equilibrium divided by the initial concentration of the acid times 100 will give you this percent ionization. We're going to work some of these later in the sessions. Remember the 6 strong acids. There are 5 monoprotic, and then there is 1 diprotic. That just means they have 2 protons to donate instead of 1 proton to donate. So you could go to HSO4 minus, or you could go to SO4 minus if you lost the second one. For monoprotic strong acid, the hydronium ion concentration will always equal whatever the original acid concentration was. So if you have 0.1 molar HCl, then when you get done, that's going to be the concentration of the hydronium ion, and then the pH would be the negative log of that, would equal 1. Since we said it's like 2 in a billion water molecules that auto-ionize, the effect on this is negligible. So that's why we don't include that water molecule in the calculations for these equilibriums. And that is the end of part 3.